Hello, everybody. This is Dr. Richard Smith, and I am here with fellow board member Ray Tomes once again to continue to dig deeper, Ray, into your 60 years of fantastic work on harmonics theory. Good to be with you again.
Yeah, nice to see you again, Richard.
I think people are taking an interest in what we're doing.
Yeah, a lot of nice comments on the videos.
I agree, and that's great to see. And it's great to see, especially because it's not easy to follow all this work.
No, it's not. No.
So it's encouraging to see people sticking with it, and expressing interest. So, we've had a few sessions now, and I think we've introduced the basics of the theory in a pretty comprehensive way, and how you came to it, and how you developed it. And then now today we're going to get into actual scientific data, observations that support the theory.
Yep.
Is that correct?
Yes. Can I make a couple of other comments there?
Yeah. Any opening remarks? Yeah.
So a couple of people kept asking, when are you going to predict the share market? We're not, but we will get to some share market cycles eventually. Not.
So this does have implication for the markets. I mean, you started out in economic data, right?
I did. Yeah.
But that's not our focus, and the foundation certainly provides plenty of, content around market analysis, but that's not the primary focus of this unique series of talks.
Yeah. And the other thing is, some people have said, just let me talk and get it, go fast through it all. And, and don't, Richard, keep stopping me. Now, I think it's right that you do keep stopping me, and you make sure that it's clarified for you. And if it's clarified for you, then other people are going to be able to follow along as well. So I think that's very good. I think that's important that we do that.
Thank you. I appreciate that. And I mean, for people who are able to follow it faster than others, bear with us, because we want as many people to understand this as possible.
Yep.
So great. Well, let's get started. And don't worry, we're not going to spend a lot of time on these early slides again, but definitely watch parts 1, 2, and 3. But just to refresh everybody's memory quickly, the basic idea, the basic theory, go ahead and tell people, Ray.
Yeah. Okay.
What this means.
I went through a couple of different things until I arrived at this fairly early in the piece, in the late 80s. I first jokingly at a conference of the Foundation for the Study of Cycles said, "What's the longest cycle? I don't know, perhaps it's the cycle of the universe." And then I went home and I said, "Yeah, it is, isn't it?" And so I came up with putting it in this form. The universe consists of a standing wave, which develops harmonically related waves, and each of these does the same. So to clarify that, a standing wave is like when you pluck a guitar or hit a drum, and that sort of thing. And the standing waves are well known in physics, and it's well known that standing waves will develop harmonics in any nonlinear system, and the universe must be a nonlinear system, or we wouldn't be able to see it. So that is the case. And what's unique about the harmonics theory is the last line, and each of these does the same. So that's what's unique, and that develops this unique pattern of harmonics that's been predicted, and we've discussed all of that. So now we're going to look at some specific scales in the universe, from the very large up down to the sort of solar system.
So before we get onto that, Ray, one of the things that's striking about this is that you're starting at the top.
Yes.
This is kind of a top-down theory, if you will, whereas all of science today is, so-called bottom-up, right?
Yeah, absolutely. Yeah, it's a very important point. In my view, we will get to the particles later on, but I love saying to stir scientists, I love saying, well, you think that your particles are the fundamentals of the universe. In actual fact, a stock market cycle is just as fundamental as your particles. And they laugh at that because that's so funny to them, but I think it's true. Because the largest waves develop the next largest, and the stock market cycles are somewhere in the middle. And then when you get down, you don't get particles until long after you've had stock market cycles, although you don't necessarily have to have a stock market. But that's how it goes, yeah.
I mean, I guess one of the things that's always been unsatisfying to me about the kind of scientific bottom-up paradigm is the role of the observer, right? Like, where did this observer come from that's able to see the particles and analyze the particles, et cetera, right? And I've never been satisfied with the answers that science has to offer, which is essentially that these are emergent properties, quote unquote, and AI is more human than us humans, right?
Yeah. AI would be a fun topic, but we probably won't get into that. But yes, the other part for sure. I agree. In standard physics, they've managed to pick up a bit of fluff along the way that doesn't belong, and people keep repeating it. And the very wise ones know that it's not true, but they can't be bothered spending 50% of their time pushing all that stuff down all the time. So we will have to have a session on the things in physics where slightly wrong turns were taken and where some extra stuff was kept in that didn't need to be, that should be thrown out. And this thing about the role of the observer and things that are, what do they call it, entangled and all of that. There's a whole lot of wrong stuff on that. And I've had contact with other people who've totally disproved that, you know.
Yeah. Good. All right. And then you developed your harmonic theory, and you were able to generate these, basically, what would you call these data points here? Are these...
that particular one is how many ways each harmonic can be made.
Right.
And then when we start dividing it out, we get the strength of the harmonics.
And through that, you developed a whole series of these harmonics, and were able to measure their strength by how high they are here.
These are predictions of the theory about how relatively strong the harmonic should be. Now, we can't really compare the ones on the left of that diagram with the ones on the right. It's just meant to compare ones in the general vicinity. And so we see that 12 and 24 are very strong, and 14440 and 2880 are strong, and 17280 and 34560 are very strong. And there's quite a few other strong ones there, but there's lots and lots of other ones. So down the bottom, and especially when we get to that one where it's got 3 whole rows of it, there's you'll see how much black there's appearing in the top one. The 2 bottom ones only start at 0.8, whereas the other ones start at 0. So there's a whole lot more black below that. And so what that means is this whole background of frequencies, which is something like white noise, that's present throughout, and there's just these few frequencies that stand out above that. And so we can understand that there's much more in the universe that we don't see than what there is that we do see.
Very good. All right. Well, let's get into today's insights.
We did this one before. Galaxies form megawalls across space. I got very happy when I first saw that one. At this stage, they went out about almost half the distance that the universe sizes, according to the Big Bang. And we can see that there's very regular structures in space over that interval. Now,
so is this saying, Ray, that there are 600 galaxies that are about 120 megaparsecs from Earth?
Yep, that's right. And and then there's a lot more just above and just below that. So there's huge numbers compared to what there are in the troughs there. It was a big survey done. I'm not sure how many galaxies they had in total, but it was a big survey done, and very interesting results, and good work. So I tried to get the data from this, but I couldn't get contact with anyone to get the data. So I basically read all the points off the graph there and put them into the computer. And then the next graphic shows the analysis of that. And you can see that there are harmonics of the original one there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The 11 is important because there are some ratios of 2 and 3 there, but a ratio of 11 is predicted to happen just after that one. And that does lead us from the very big geological cycle times down to the mass extinction cycle. And there's a ratio.
Okay, let me go back here for a minute because I want to make sure we understand what this is. So,
so those peaks,
these peaks look very rhythmic, right?
They are.
And they look very equally spaced.
Yeah.
And what is this distance between these peaks?
586 million light years.
Okay.
And the Hubble constant is known accurately enough.
A special number?
Because the geological cycles also have a 586 million year cycle. And what that shows is we're seeing two aspects of it. We're seeing these, I believe, form on the nodes of these standing waves in space. And the geological cycles tell us the oscillation period of those standing waves. And when the oscillation period in years is equal to the distances in light years, then you know that it's a light speed phenomenon. And I've had arguments with people who said I do numerology, and eventually I've managed to show them, oh yes, that is the formula for the speed of light and the wavelength and the period. So this thing here on its own is, in my view, an excellent argument against the existence of the Big Bang. The fact that these waves have existing in space out to very large distance, and an appreciable percentage of the size of the universe, according to the Big Bang, and they're very regular, and they're continuing, obviously, to exist over a long period of time. Because
if the Big Bang were true, we'd expect these cycles to not be here, to have it to be more homogeneous and more uniformly distributed.
Well, there's two things. On the one hand, they shouldn't be able to exist for long periods of time. And secondly, they shouldn't be that regular out to such a large distance.
Yeah. And why? So these numbers down here, Ray, do we care at 100, 200?
No, we don't. We don't really. The astronomers make assumptions. They assume that all their theories are correct. And the way rather than give you raw data, they give you data after passing through several filters of their stuff. So first of all, they're actually measuring red shifts, and they could have done that as red shifts. They then turn red shifts into velocities, and I'll argue that they're not velocities. And then they turn velocities into distances using their strange units. Now, I agree that they are measuring distances. But they will agree, the astronomers will agree, that these units, that these spacings are near enough to 586 million light years apart.
Okay. So essentially, we see a structure in the universe in the distance, not just time. We're talking about distance also.
Yes.
That these harmonics show up not just in time, but also in distance.
Yeah.
And that this distance is 586 million light years from peak to peak. Okay.
And from Professor Afanasiev's geological studies, he gets 586 million years for one of the very strong cycles.
Right.
And so
this is the main 586 million
year
cycle that we saw in the previous chart. And then these are harmonics.
Yeah. So for example, the fourth harmonic there would be 293, 146 point something million.
1/4 of the 586
light years. Yeah. Now that's in the light years, but we find that one in the geological record, and we find it in temperatures and carbon dioxide variations over the last 600 million years. We find that one quite strong, number 4. And number 11, we find that showing up in some of the smaller ages of the geological deposits, including mass extinctions. That one gives us the mass extinction. So the fact that 11 is moderately strong, that's good support, because that should be the case according to the theory.
So if I divide 586 million by 11, I get 53 million.
That's correct.
Roughly.
And half of that because we haven't gone that far, but half of that is in fact the mass extinction cycle, 26.65 million years.
26.6465 million years.
So those are, so we are finding agreement between the structure in space and the structure in time that we've got from geological deposits. Good evidence for the fact that these are standing waves.
Very good. All right.
Now, going back in the 90s, I used to post on Usenet. We didn't have, this was before the World Wide Web existed. And perhaps go to the following one first, and then we'll come back to that one. I posted this table on Usenet in 1994, saying that it took me a while to work this out, because originally I'd found there is this, you'll see on the right-hand side there, 72 kilometers per second, a red shift is predicted to be there. And the ones with asterisks are the stronger ones, which when we go back to the other one, we'll see. But the 72 kilometers per second one was found that galaxies and clusters like to have difference in velocities that were near multiples of that. And no one could make any sense of that, because they were supposedly all just orbiting each other in some random way. And it would mean that we were in an especially privileged place in the universe. And generally, cosmologists are against us being in an especially privileged place. And I would agree with them about that.
I got to stop you again, Ray. So
yeah,
just to see what what are we looking at here? So this is measuring.
Okay, well, I'm just starting with the 72 kilometers per second. So we're going to come back to this. That one was found as an observation. But when I tried to do the calculation, I thought, okay, I've got to divide the speed of light by, I worked out 2880 was the most likely one, and I divided that, and I got 104 kilometers per second if I took the speed of light and divided it by 2880.
Okay.
And for a while, it didn't work, and I couldn't work out why. And I thought maybe we're looking diagonally across. If we've got a square structure of galaxies, then if we look at the diagonals, we would get the square root of 2 divided into that, and that comes out to about 73.5. It didn't agree. It was definitely close to 72. So for a while that didn't work. And then I remembered Einstein had this thing called a velocity addition formula. And basically, let's say you do have a galaxy that's moving at 72 kilometers per second relative to us, and then another one that's another 72 relative to each other. If you keep adding them up, you don't get to the speed of light. He's got an addition formula where it gets a little, each time you add it's a little bit less, and it never gets there. And once I realized that, I worked out, okay, what happens if you do that 2,880 times? And the answer is you get to 0.693 times the speed of light. What's so special about 0.693? It's the natural logarithm of 2. It turns out that if you do multiple steps of galaxies at 72 kilometers per second, after 2880 steps, the total red shift is exactly 1, which means the frequencies are related to the frequencies on Earth by a ratio of 1 to 2. And once we understand that now in harmonics theory, you've seen ratios of 2 are the most common ratios that we get on everything. So if we say, and I'm arguing that these are not velocities. It's unfortunate. Everyone quotes them in velocity units, so I do that so we compare to what everyone's quoting, but they aren't really velocities.
So basically, this is looking through a telescope and measuring how fast something is moving away from us based on the redshift observed. So if the redshift really was velocity, that's a velocity you'd get. But if it wasn't velocity, if the redshift's got another cause, and I don't think we've dealt with that yet, but that's something we should do in the future of what's going on. But what it means is that if you have a huge wave in the universe, there's an important distance at which the frequencies change. The frequencies over time are changing, and so you get this just that distance at which that becomes exactly double is an important distance. And so the formula for calculating these is that we take
you can see number 1 is 0.693147. That's just the log of 2. So what that says is that log 1 plus z is equal to log of 2, or in other words, 1 plus z to the power of the harmonic equals 2.
Okay.
So that's the basic formula. Now, I'm not the only person to get a formula like that. Helton Arp had a very similar formula for doing calculations because he didn't think it was velocity also. So he said, this is the way you do it. You take the log of 1 plus z, and that gives you the correct measure. So what I'm doing here has been done before, but only by people who don't think it's velocity. So when we do that and calculate from the very strong harmonics, so all those ones on the left of each of the 2 columns are the very strong harmonics, then we calculate out what's the equivalent velocity of the red shift. And I've marked with an asterisk the very strongest ones. And so 72 was the one that was observed a lot by Harp and also by William Tift. Now, so once I understood that and got that correct, I worked out, okay, I put this table onto internet and said, I predict that these values will be there. And one very kind astronomer said, you need to go and read the work of William Tift. And he gave me a reference to one of his papers. And in that paper, William Tift said, in addition to the 72 kilometers per second quantum, there's other ones of 36, 24, and he basically listed all those values down there, not the 2. From 3 to 72, he listed them all but 1, and he had one more that's not in that list. So over an interval, he had 11 out of 12 that I had. Now, if we go back to the previous diagram, that's the same thing, but in graphic form. You can see the 72 kilometers per second just past the middle there. And then you'll see that 2.672 kilometers per second, that was one that Tift mentioned that I didn't list in that table, but it was the next strongest one that I didn't list. So I cut it off somewhere in almost exactly the right place. And so, and these larger values, I've done the smaller ones in kilometers per second, I've done the larger ones in this delta log 1 plus z. And a number of those other ones have been reported by people, particularly those 2 big ones, 0.05776 and 0.02888. Those ones have also appeared in different studies that people have done.
Mm-hmm.
So, okay, what does that mean? It means that there are these structures in space. And the thing is, we've then got to try and work out what are the, how does that relate to our nearby galaxies? So, for example, Andromeda Galaxy, originally they worked out the distance, but they don't expect its red shift to be very meaningful in terms of the distance, because they've got each galaxy thought they have some little bit of a velocity anyway, and so that doesn't. It's when you're going a huge distance, the velocity is a good measure of the distance, but for short distance, it's not. Can we pause a sec there?
Yes.
I need to work out. I'm just doing a calculation here, which I'll try and do clearly. 72 kilometers per second, with the Hubble constant being 71.2, so it's 71.1 kilometers per second divided by 71.2 gives 1.0126 megaparsecs times 3.26 x6 equals, that gives us 3.3 million light years. Okay, so so we can restart and I can do that. So that's 72.15. Oh, I should mention with Tift, one value he published on that was 72.135. I've got 72.153. And he said it's plus or minus 0.01 or 0.02. So it agrees excellently with that. Later, he published a value of 72.45, but he showed a graph of it, and there were multiple peaks, and it could be 72.15, 72.45, 72.75. So those values, and the reason there's multiple is that you can use the difference between them. The beats, they come from the fact that there are these big, huge clusters. And when you look at a bunch of galaxies, and you've got a cluster there and a cluster here, and there's a lot of nothing in between, how many you count in between there of those, you can get one out. You get 72.45 by counting one out. I'm not blaming him for that. He's doing a fantastic job of measurement. But from that one, you can actually show that this is correct. Now, that 72.15, if we take it and we divide it by the accepted value of the Hubble constant, then we get just over 1 million megaparsecs. And a parsec is 3.26 light years. And when we multiply it out, it turns out that that is 3.3 million light years. Now, so that's the interval. Those the peaks of galaxies that are at that interval are 3.3 million light years apart. Now, when I first did this work, the distance to Andromeda was believed to be 2.2 million light years. And in the cycles periods that pop up and things, we do get 2.2 million, and 1.1 million is a very strong cycle that occurs. Now, what's the next graph after this? And the one after that. Darn it. Have we got magnetic reversals in here? Try one more. Yeah, that's the one. The magnetic reversals of the Earth, the black and the white in that upper graph are showing when the North Pole's at the top, or when the black means the North Pole's where it is now, white means the South Pole's where the North Pole is now, and they flip over. Now, probably it's a bit incomplete out the right-hand side, but they get these things by, there's seams like in the Pacific Ocean, the Atlantic Ocean, that comes up and it goes outwards. As the magma sets, it gets the polarity that the poles have at that time. And so when they look down the sides of these things, there's like barcode patterns down the sides of these seams where the stuff comes up in the oceans. And they look like that, and the mirror image of it on the other side. So it's fantastic work that they've done. And then they say that they're not cyclical. But what I've done there with those orange ones, I've put them at regular intervals of 1.11 million years.
Okay.
And see that they agree pretty well. Most of them are either on a black blob or a little cluster of black blobs, and the spaces between them mostly white. So I believe that that there is a 1.11 million year period in the magnetic reversals. It's not the only period. The green ones show there's about a 9 million year period as well. Okay. And there are other shorter ones, because otherwise there wouldn't be these other ones. So there's room there to do cycles analysis if we can get the data on that at good intervals. That can be analysed further and show that. Now, the 1.11 million years is also interesting because it's an energy exchange between Neptune and Jupiter. It's actually all the other planets, but Neptune and Jupiter is the main one, that there's an energy exchange between them, and that has an interval of 1.11 million years. So that's agreeing very well with us. And I believe the reason that this happens on the Earth is because of this energy exchange of Jupiter and Neptune. And it's a more complicated thing, which if we talk about the cause of the sunspot cycle sometime, a similar thing happens inside the Earth, I believe, that the magnetic field of the Earth relates to what proportion of time the matter of the solar system spends above our equator and below. And that causes internal convection currents to happen in the core, and leads to these reversals happening. So that's another whole complicated story. The important thing here is that there is a 1.11 million year interval, and a 2.2.
And you are relating that back to this.
Now that would be the 24 down there, right? Which is a third of the 72, because the 72 gave us 3.3.
Okay, right here.
Yep. So those ones there would be 3.3 million years, and that's a
so this
1.1.
is the 3.3 million light years, and this is the 1.1 million light years.
Yes, that's right. So we are finding, so that's TIFT found that, so it is there. It's there as a spacing of the galaxies, and it's there as a period on the Earth. So that means that we've got another case here where we're finding that large wave structures exist in the universe, and the periods are recorded over long periods of time. How many million years have we got on that thing there? It's hundreds of millions, isn't it, I think? Go down a couple again.
Sorry. Is it?
Two more. No, wrong way.
Oh, this.
We'll come back to that one. One more. That's, yeah. So, oh, yeah.
This is where we were.
Yeah, but we did the magnetic reversals, which was after that.
Yeah, we did this one.
Yes, that's right. Now, so I just want to see that's 80 million. We've got 80 million years of that. So we can say...
I see. That's what this is along the horizontal axis
you'll
here.
find that a lot of these people that do geological and other things run time from right to left. I have no idea why they do that, but they do. So you've got to watch it on graphs of geological stuff, whether somebody's done it for the general public and done it the way we normally do it, or whether they've done it for geologists where they do it backwards. Yeah.
Okay.
Okay, now...
All right, so we skipped over these two. Do you want to talk about this one?
Yeah, that one was somebody else. Several other people, when Tift kept finding the same stuff over and over, and people said, no, it can't be like that. It's impossible with how we understand the universe works. The reason is the way you understand the universe works is wrong. So a number of other people did other studies. This is one of those, and it gave 71.1, not too far from 72. Another one, they got 37.6, which was close to the 36, but they had plus or minus 2, so it gave the 36. Every single people, there was Guthrie and Napier, I can't remember who this one is, that did these extra studies, found that there were these things, and you can see it's very solid there. Those peaks are very clear, very regular. They say that's the raw data. There's no smoothing has been applied. So it's very definitely there that there are these regular structures. And it clearly proves that galaxies don't actually have velocities at all. Because if galaxies really had velocities and they're all moving randomly relative to each other, this thing would just be a wobbly line, a virtually flat line all the way through. So the fact that that's not the case, that's evidence for that as well. So all these things are evidence against the current understanding, the Big Bang, and evidence in favour of an entirely different thing. Now, one before that, I think. No.
That one or this one?
That one, yeah. Now, we got those velocities there. They're interpreted as velocities. I'm saying they're not velocities, but the red shift correspond to these things, 3, 6, 9, 12, 18, 24, 36, 72 kilometres per second that Tiff found. These are the velocities of the planets around the sun. Now, ignore the outer planet for the moment. Ceres, Mars, Earth, and Mercury are all on exact multiples of 6 or 12 kilometers per second. Venus misses by 1. It's on 30.
Hold on. Ceres is on 18, and Mars is on 24. Earth is on 30.
Venus on
is
35.
on 35.
So missed by 1.
Okay.
Yeah.
And Mercury's on 48. So they're all multiples of 6.
Yeah, so the planets in the solar system are going around the sun in a way that means that some of these waves that are coming from galaxies that are at the 72 kilometers per second thing and other ones are supporting their material structure at being at that velocity when they go at their maximum. So according to these other guys, all these things are coincidences. You know, according to the scientists with the standard views, these are all coincidences I keep finding. My answer to that is always, yeah, I've got some more. Now,
I've got some more. So these are redshifts.
Yeah, those in the case of the galaxies, they're redshift. In the case of the planets, they are actual real motions around the sun.
Okay.
Now, Jupiter, Saturn, Uranus, Neptune, Pluto, that doesn't work for them, right? But we'll get to another part where we look at this other stuff in the solar system, and we'll find that something else works for them. So there's one rule for the giant planets and one rule for the small planets, and they both slightly work on the other thing, but they only work on their one. Okay, we can carry on forward.
So moving past the magnetic reversals, we're now going to get into
Now,
number of
people have
star
done-
pairs at distance.
yeah, so later, after this, we'll get to Bode's law, which is about the planetary distances. We did the galaxy distances, but I didn't find that anyone had ever done the distances of the stars to look for, is there periodicity in that? So this was a long time ago that I did this. You can tell from the fact I did it with asterisks, not pretty graphics.
Mm-hmm.
And again, I put this on Usenet at that time, and I did it from Norton Star Atlas. And I got laughed at by the astronomers. And I said, well, Norton Star Atlas, the values were the best values at one time. And I took all the stars that were within a certain distance so that their parallax can be measured. So parallax, as the Earth goes around the sun, from the two different sides of its orbit, we can see the star is at a slightly different direction. And from that, we can work out the distance to the stars. Now, going back 30 years or so, or 40 years, the data was not so good. But now they've got some special ones in orbit just doing this, and they've got the accuracy now is like 100 times better. It's phenomenally improved. So a much better version of this could be done now, but it doesn't matter because the central features are there. It's basically a histogram of how many star pairs. I took every pair of stars within that space. So not just us to the planets, to the stars, but each star to each other star.
Right.
And this is the histogram I got. Now you'll see the biggest one there. As you go out, of course, there's more. But you'll see the biggest one there is just short of 12 light years. One of our strong harmonics.
How many stars did you?
1, 2, 3, 4, 5, 6, 7, 8, 9. I think those are individual stars.
Okay.
9 pairs have that distance. And that's a very strong harmonic. 9.6 years, you know, is the Canadian lynx cycle and some other things.
Right here.
Yeah. 8.9 there. 8.88 is a strong cycle that Dewey found. There's one just under 8. It's about 7.9 something. Is the next one along.
Okay.
Yeah, and then 7.12. There's a group of cycles.
Gotcha.
5.93. There's some. There's some around 5, and 4.45. There's a couple. And you'll notice there's one at 2 years and 3 at 3 years. Those are some of the strong cycles that, if you compare that to Dewey's strong cycles, it's an incredibly good match of all of those things.
So I mean, did you study 100 stars or 1,000 stars or 10 stars?
I did all the ones within that were within a distance that the parallax could be measured sufficiently accurately. So it's a complete table. It's a lot less than 100.
Okay.
Yeah.
So and you found that a lot of pairs have a distance of 11.86 million light years.
Yeah, that's right. No, 11.86 light years, not
11.86 light years. Okay.
Yeah. So that's
okay. Wow. I mean, those numbers really do line up with Dewey's table of cycles.
Yeah. Now, what does it mean? It means these people that study the stars influence our lives, that do astrology. They're right, they do, but not in the way they think. The waves that are going through these. Now, the next step I said is, okay, let's look for, I took the 4.45 year one, and I said, let's imagine that we make a series of planes going across in space that are that many light years apart.
Okay.
And I made those planes. I pointed them to every direction in the sky, right, to see how well it fitted. And I changed the period, and it turned out that at 4.43 light years, you get the best fit of all of the stuff as a series of planes that things out multiples of that. Now, what I did is I made it do that all over with 4.43 light years, which we know is agreeing with Dewey's cycle of 4.44 years and mine of 4.45 that I got in my studies. So those three things are all agreeing with each other. And then what we do is I pointed it in every direction in the sky. And and I didn't have any 3D graph paper, so I used a ping pong ball. Somewhere I hope I've still got it. And on the ping pong ball, I marked everywhere where there was a very strong relationship in that direction. What I was expecting to happen originally was that there would be 3 directions at right angles to each other, which was a grid, that the stars were on a grid. And that wasn't what happened. There were actually 5. 3 of them were approximately at right angles to each other. And 2 of the others with one of the originals were also the same, not quite so strong. But so the 3, it doesn't, I then realized if you go to the next one, so on the left, I'm showing if you had a regular square grid, I'm not trying to do 3D, with a distance 1 and distance 1 that way, the diagonal will be 1.414, the square root of 2.
Okay.
And that's not a good harmonic. So that's not going to fit with harmonics theory. However, if we twist the thing a little bit like on the right-hand diagram, it's very nearly the case that you get 4/3 one way and 3/2 the other. In fact, you can see if you average those two, you get 1.417 compared to 1.414. So it agrees very well. So if you get a slightly distorted cubic grid, then, and that's what was actually there. That's what the stars actually do. So does that make sense?
So what you're saying is that you're looking at the distance between stars.
Yeah.
You know, and then you're creating a grid at that most commonly found distance.
Yep.
Right. But you're shifting the grid a little bit.
Yeah. So originally I just did planes to see if they lined up in planes,
Right.
and they did. But the 3 planes I found weren't at right angles to each other like that. They were at an angle like that.
Got it.
Now,
Okay.
I told this to one of the famous astronomers, what's his name, at Princeton. He does a lot of cosmology stuff. His name will come to me at some point.
Okay.
Anyway, I had a chat with him. He'd agreed to meet me, but he was madly busy preparing for a conference that he was doing. And so he was only half paying attention. And when I told him that the stars are on a grid like this, he says, but that's not possible because they go around the galaxy, so they are going to get messed up. And I said, yeah, well, everyone said it wasn't possible with Penrose's 5-fold symmetry to tile the plane. And he said, that's true. He says, it could be something like that. And I said to him, well, in actual fact, if you've got a grid like that of stars, as they go around the galaxy, rather than imagining it to curve around like that, you actually go around with it in place. Then each of the stars does the same sized orbit. So the ones that were towards the center of the galaxy overtake the outer ones and become the same distance, and then they become the inner and outer opposite. So they actually, the whole formation can actually stay in place if it does that. That I'm not doing a great job of describing that, but it is possible for stars to remain in more or less a grid while they orbit the galaxy. They don't get out of place. Now, some of the stuff can be tested. What was that? What was the other thing I wanted to test? Over the last few decades, they've started to make very accurate measurements of the motions of stars. So accurate that if there's a planet orbiting it, the planet going around the center of galaxy, center of mass, the star goes slightly further away and slightly closer to us. So it has a tiny velocity. And these velocities aren't in kilometers per second, they're in more like meters per second. And they can measure them that accurately, and that they can detect planets. And a lot of planets were discovered this way. They've got a couple other ways now as well, but it's a very clever technique. But those velocities being measured very accurately like that, if I'm right that these waves are causing the stars to stay in place, then it should be that there's slight accelerations due to these big electromagnetic waves that push the stars back into place if they start to wander off. So I think that should possibly be detectable, because I'll tell you why that is. If it's a 1.4, if it's a 4.44 light year, or 4.43 light year spacing, but if we look at the nearest star, Alpha Centauri, it's 4.31 light years away. So it shouldn't want to wander too far off that. So in my view, there should be a slight acceleration pushing that back towards the 4.44, it will overshoot and come back. So it's like a crystal. If we have a crystal and we hit it with a hammer, vibrations will go through it. So the distance between atoms and the crystal will do slight variations. So it's that same thing that should be happening. And the bonds of the crystal are these 4.44 light year are the bonds of the stars holding them in place. So it's possible to test that. It'd be good if someone took that on as a project. It's something that would be the sort of thing that Radiance Trust would give a scholarship for someone to do that. Right?
Very good. So, duly noted.
Yeah.
So is there anything significant to the fact, these 3/2 and 4/3 numbers, which are harmonics, right?
Yeah, they are. If you look at Dewey's table of the common cycles, if you go down one way, it's divided by 2, and the other way is divided by 3. Right. I can't do this with mirror image. Then if you go, if you take the different directions, you'll find there are cycles nearby that are 3/2 and 4/3, because you move 2 2s one way and a 3 the other way, or 1 3 one way and a 2 the other. So those, in all cases where you have a very strong harmonic, 4/3 and 3/2 times that will be also strong. Yeah, so very significant.
Okay, very good.
Okay. So that was, so what we're looking now is the waves. So what was that one we did?
We just did 663, the stellar grid.
So with the star distances, we've found that both the distances of the stars like to be lined up on these intervals, and we know from Dewey's common cycles that the cycles periods agree very well with that. So again, we've got electromagnetic wave would have both the wavelength and the cycle period in agreement like that, exactly as we found. So this is the third case of strong evidence for large standing waves in the universe. So now we're going to the next one, which is the planets. Bode, it was called Bode's law, but then they called it Titus Bode because Titus actually did it first. And in his system, this is different. What I've got here is the Harmonics Theory system, but Titus Bode, he cheated slightly, but more or less he had a sort of doubling of planetary distances. So like from Jupiter, Saturn is double, into Uranus is double. And the next double would have given where Pluto is, but in actual fact, Neptune was discovered there. But you can see that's plotted to scale there. That's showing a 163 light minutes. I've called it a 160-minute wave. And that shows you that Saturn, Uranus, Neptune, and Pluto, which was a planet in those days, at very, very accurately steps. Now, on that other graph, I said the inner planets do it on velocity. The outer planets do it on this wave. And you can see that it's very strongly fits that. And Jupiter on the half wave. For the inner planets, they don't fit so well here. You've got Mercury, Venus, Earth, roughly 1, 2, 3. Earth a bit short, and Mars is rather too far. But is that just Ray imagining that, or is it something else? Maybe the next graph will show us. In this one, I put the distances of all the planets from the sun, and I use that Kotov's method to find common factors and multiples of them. The two strongest ones there, now I've marked with triangles values that those are exact ratios of 3, 2, 7, 2, 2, 2, 3. And they're the strong places where Kotov's method says something's going on here. And those two there are the 80-minute and 160. So the 160, the biggest one just past the middle, that's the wave through, no, the next one. Next one's right, yeah. So that's the one that gets Saturn, Uranus, Neptune, Pluto. The previous one to that gets all of those.
Why are you saying it's 160?
160 minutes, 160 light minutes from the sun.
Okay.
So we're doing light minutes.
I don't see 160 on this. Is that the vertical axis? It's not labeled or something?
Yeah.
Okay.
That's an astronomical unit. An astronomical unit is the distance from the Earth to the sun, and light takes about 80 minutes to do that. So those are 5 and 10 astronomical units, okay, or 80 and 160 minutes.
Mm-hmm. Okay,
slightly
gotcha.
over those figures. And then if we go back down here, we get 2 on the left, 2 bigger peaks. One of them is at 0.7 and one is at 0.35 roughly. And if we go back to the previous diagram, there's a small one there of 2.12. Just remember that one for a moment.
Hold on, Ray. You go so fast sometimes.
Sorry.
So this is 0.7. Here's the peak.
Yeah, it's about 0.73, I think.
Okay, and then this peak?
About 0.35 or 0.36.
Okay, yeah. And then?
And there's another strong one there at 0.12.
0.12, right here.
Yeah, that's right.
So those
are the 5 strongest 1, 2, 3. It's worth mentioning this one at 120 astronomical units as well. It predicts that that's a place where we might well find more matter in the solar system. It's a long way out, and it's hard to see things there, but it's quite possible that that's some of the stuff that floats around the periphery of the solar system.
Okay.
So if Harmonics Theory is right, that should be the case.
Okay.
So go back to the previous one. Now, so down the bottom there, I've got those 2 strong waves for 9.8 and 4.9 on that first diagram, which is 163 and 81.5 minutes. And then the other waves I've shown there is the 0.35 astronomical unit, which is 5.8 minutes. And that's the one that picks up those planets, roughly speaking. And then I've got another one that's a third of that. Now, let's link all this together. So some of the cycles that are commonly found in this range are 3 minutes, 6 minutes, sometimes 12, 40 and 80 and 160 minutes, and sometimes even 20. So those waves are found as periods and cycles in a lot of things, but they're also found as distances in light time. So the light time to get from the Sun to Saturn is 163 light minutes, and 163 minutes light will travel that distance. So a standing wave oscillating in 163 minutes will go through Saturn, Uranus, Neptune, Pluto. So this is again confirming that that we're getting both a distance structure and a time structure that agrees with that. And so let's, in the case of 160 minutes, a lot of different things have been found with 160-minute periods, and we'll deal with some of those. One of them is a solar oscillation, and it's been found, the Americans have found it, the Russians have found it, and they did it from the South Pole as well. And the phase of them are all the same. And at one stage, they thought, this is something to do with the Earth, because it's almost exactly a 1/9 of a day. 160 minutes is a 1/9 of a day. But they've shown that the phase gradually changes over the years, and all the different measurements show the same phase movement. So it isn't it isn't connected to the day. I'll give you some other examples of 160 minutes. If you put something in orbit just above the sun's surface, it takes just over 160 minutes to go around once. So in other words, particles flying around there will traverse around the surface of the sun. If you take some of the planets, now I may get this wrong, Mercury, Venus and Earth have something going around just above the surface, take just over 80 minutes, about 84 minutes. So that's the next shorter one. Jupiter and Uranus, they are on the 160-minute one as well, the same as the Sun. Saturn is on 247 minutes, 3 times the 80-something one. So all the planets, things that orbit just above the surface, are tied into these multiples of 80 minutes. And we'll see some other examples as well. Black holes fit into that as well. Kotov, whose method I use, he came up with this thing about the outer planets first, and he studied a lot of other things. He'd studied binary stars, and he found binary stars like to rotate around each other in multiples or fractions or right on 160 minutes, and very significantly. Asteroids and other stuff do that too. There's a rotation period. There's a lot of things that follow that one. The short one I've got down there at 0.117 at the bottom, that's just under 2 minutes. There's another wave, which is a third the size of that one, and which when you get out past Mars, it shows you where the asteroids are not regularly spaced. I've got a graphic of that. I don't think I've got it here, sorry. But they're regularly spaced at these intervals of that one. And the explanation for where they are is that they can't be where they get certain kicks from Jupiter. It turns out the only place asteroids exist is where that method, that the standard explanation and my explanation both agree with each other. In other places, they don't agree and you don't get asteroids. Okay, let's go forward a bit. So we've done that one. Yeah. Okay, so this is the 160-minute wave that does not exist in the sun, according to Wikipedia and according to many astronomers. Now, I've put little green V's there above a series of peaks there at exactly 160-minute intervals, and you can see this is X-rays and the sun.
I don't see where are the little green V's. Oh, over here. Okay, right.
Yeah. Yep.
Okay, so these are at 160-minute intervals.
Yeah. Yes, that's right. And you can see that quite often the peaks are lining up very well with those. Go to the next one. It's even a more interesting one of the same thing, really. And I've put marks with the red there on the bottom right and on the left, showing 160-minute intervals. And you can see they don't always line up, but they quite often do. In the next graph, I've expanded that bit on the lower right. And you can see the red marks there, that there's one right on each of those. Now, that increase of that one there is an increase of 8,000% in the number of X-rays coming from the sun. In other words, it's not just a faint thing that's happening. X-rays come in giant bursts from the sun at 160-minute intervals, most commonly. Yeah.
Okay.
Yeah. So now this is what Wikipedia has to say about the 160-minute solar cycle. Was an apparent periodic oscillation in the solar surface, which was observed in a number of early sets of data collected for helioseismology. The presence of a 160-minute cycle sun is not substantiated by contemporary solar observations, and this historical signal is considered by mainstream scientists to occur as a redistribution of power from the diurnal cycle. The diurnal cycle, they mean the Earth's daily rotation. So they're saying it's wrong, it's in the daily rotation. Now, that theory was put forward early in the piece, quite validly as a possibility. It was quite clearly disproved by the phase changing on these things. If you try to put that into that thing now, they will delete it. You can't put that in Wikipedia anymore because the mainstream scientists want to ring fence their stuff and say, this is the truth. Anything outside that, it's not true. And it is quite clearly there. You saw the graphs with 8,000% increase and other massive increases in those things. These guys are misrepresenting the situation.
So these were the 160-minute intervals of X-ray production.
Yeah. Now, this is not this is not the thing they refer to. They're referring to actually an oscillation of the surface moving up and down slightly, sort of the sun breathing. But I believe that those are correct because the phase changes and that other stuff substantiates it. And the fact that things orbit the sun in 160 minutes substantiates it as well. There's definitely processes going on there with that.
Okay.
So 160 minutes is a clearly strong one. This is, I have a friend in Australia, Peter Brown. He calls himself Mountain Man, and he has a substantial website with a lot of stuff. And he's been a good supporter of me. He's the only person that's ever taken all those calculation of harmonics things, and he calculated those out. He didn't go all the way I went. Because I had to find some cunning tricks to get that far. They did a substantial number, and he said, I can confirm that everything you've got up to there is correct. Now, I went and visited once in Australia. He also is a surfie, and even as he got older, he still surfed every day. And I told him about the 160, 80, 40, and 20-minute. And he said, yes, he says 20-minute waves. He says, every surfer, every old surfer knows about the 20-minute wave. And I went and watched him surf one day, and I saw him go out a bit further and catch a really big wave in. And I was noting down the time of all these things on a piece of paper. And sure enough, 20.4 minutes after that, he went out again and caught another really big one in. So that was there. This is some data that we got from the Sydney Wave Laboratory. It's interesting that they do it because they don't want you to, they know there's dangerous times with the sea outside Sydney Harbour, big surf, and they have a lot of buoys out there that measure the rising and falling of the things, and they transmit the data to their laboratory. Now, it has a, it does it for, this is going back a bit, and it would do it for a while, then it would have to turn off for a while, transmit, then it would measure the waves again. But you can see that 20 minutes and even 10 minutes are there as part of that series from 160, 80, 40. And also multiples of 6 minutes, 6, 12, and 18 minutes are also there. So that means when you get a strong wave, what this is showing you is the correlation between the wave heights at one time and at some later time. And you can see that multiples of 6 minutes and divisions of those other ones that come 20 and 10 minutes are favoured by waves being around the same size. So those periods exist on the Earth in sea waves. There's some shorter ones in seconds as well, but that's another case of stuff. Another friend, Ross Tessine, who agrees about some of the structure of waves in the space. He found one. He found when the light was very low across the Mediterranean, you could actually see the waves. It'd be lighter and darker periods of sea. And he measured it and he worked it out. And he said that's a 40-minute wave in the Mediterranean there. So these waves are around the world responding to cosmic forces.
So, basically we're seeing all this structure in distance and in time.
Yep. And
there's really no possible explanation for that structure to exist.
Except that there's big, strong electromagnetic waves.
Because it can't be a bottom-up phenomena.
No, it's coming from the top down. Yeah, the next one after this is interesting too. It's quite fascinating. Oh, that's the black holes. Black holes, now this was done a little while ago. There's probably better data on black holes now, but I got all the list of black holes from this website, which I found in info on Wikipedia, I think. Each black dot there is a black hole. Some of them have got accurate measurements of their mass, some of them not so accurate. And so going along there is their mass of the black holes.
So these are masses along the bottom.
Yeah, that's right.
Here. Yeah. Okay.
So they range from like 1 million over there to more than up to 3 billion over there. And so they put them in. And now I've marked here, you can calculate from a black hole's mass, you can calculate its radius, the Schwarzschild radius. And if you do that, I've put some of these common ones. We've got 3, 6, and 12. And I've also put 80, 160, 320, and 480 minutes. And you can see that black holes quite like to favour some of those things. So that means that it's quite clear that these are universal waves because these other black holes are mostly in other galaxies. So most galaxies have a black hole at the centre, that's the fact. And they're usually in that range somewhere. You can see a lot of them in the middle there.
Why did you skip over this middle section here?
I haven't put one there, but there is a lump there, isn't there, at about 2 by 10 to the 8. That corresponds to about 30 to 32 minutes. I'm not sure, somewhere in that range. It's not a particularly common cycle, but it's obviously a size that likes to appear there. So it may be a way for that one that I've missed.
Okay.
Yeah. Now this one is blood sedimentation. Now this is the whole story of blood is fascinating. When they do a lot of blood tests, they spin it in a centrifuge to separate out the components, and they do tests on the different ones. Someone started recording, and they said some days it takes longer than others. Why is that? And they started recording the times, and they did this in multiple laboratories around the world. And it turns out they all take longer on the same days and less on other, and so on. And there's this thing's wandering along. It's related to this. It's related to the sun. But this particular one I liked because they actually put a laser on to measure how fast it was sedimenting, and they measured instantaneously the rate at which it's doing it. And after a few little wobbles, it settled down to doing a little jerk every 3 minutes. And those ones are just under 3 minutes. They're showing a 3-minute wave. So presumably the sun or the universe is influencing blood in the sediment that's being sedimented. Now, it doesn't just do it when the blood's in there. It doesn't when the blood's in your body. We are affected by these things. You've heard of the 90-minute sleep cycle. It's really about 84 minutes. It's the what I call the 80-minute cycle. And we go waves of deeper and shallower sleep over that time. Mm-hmm. So those are showing up, and that's in the 3, 6, 80, 160 minutes are showing up and influencing everything in our lives. Another fellow that was on the Cycles Foundation, Dardick, I was going to try and do some cooperative stuff with him, but we didn't get to it.
Yes,
we didn't.
He wrote a book, right? Irv Dardick, I think his name.
Yeah. And he did these pictures of waves with waves on top of them. And the diagrams he did were quite graphic ways of showing what I'm described at times. And he was training Olympic athletes. And I think he was using some of those cycles, burst mode. So you do a minute or two, and then you have a minute and every 3 minutes or 6 minutes or whatever. And you do it for that period of time. So those things can help to coordinate yourself with the cosmos if you can synchronize.
Interesting.
Yeah.
Okay. All right, one more.
Is there any more? Oh, yeah. Oh, well, that one, this is a correction to my correction. I'm not sure now exactly when I did the longest cycle in one of the earlier talks, I did use that 586 million year cycle there, and a number of these other ones, a lot of Dewey cycles on not the bottom row, but the previous two. When I had a discussion in the BORT Forum BAUT, which has changed its name, I had some long discussions there, and one person asked me a lot of questions that I answered. And how did you calculate this longest cycle? And I said, I put these values, and that's the values I listed there. So they may be the correct values. The ones I've told you, I gave you a couple of diagrams, which were slightly different values. They did range from the 586 down to some of these others. So these may be the correct ones. Now flash it away quick, please. We can go to just talking now.
Just to review briefly, we saw the structure in the distances of galaxies, the 586 million light years, right? We saw harmonics of that structure, that these also played significant roles in other phenomena, right?
Yep.
We looked at redshifts.
So this is galaxy spacings now.
Spacings.
That was supergalactic clusters, the other one. This is galaxy spacings.
And we saw a structure here reflective of the harmonics.
This is my predicted structure. Those two are my predicted structure.
Okay. And then that's
an actual measured one. And there's quite a few different ones that have been done of that.
Right. We saw more structure here.
That's showing how the planetary velocities relate to the distances. And we'll come back to that when I do the universe-wide web. I haven't done that with you yet, have I?
No.
That's a fun one.
Okay.
How to link these diverse phenomena together.
Saw some cyclic structure in the magnetic reversals.
Yep.
Pairs of distances between pairs of stars.
Yep, and they show clearly that the Dewey cycles are present in the wave structure of the stars.
Wow. You hypothesized about a stellar grid?
Slightly womped one, yeah.
Slightly womped?
Yeah.
We talked about more evidence of standing waves in distances between planets, especially the outer planets, right?
Yes. Yep.
Same thing here.
Yep, that's right.
We looked at structure in the sun itself.
Yep.
Solar flares on 160-minute periods and X-rays on 160-minute periods. Wikipedia doesn't believe it. And structures of waves in the ocean.
Yes.
Also showing such patterns, and black holes
Black holes, yeah.
and blood
Blood, yeah.
sedimentation.
It pops up everywhere.
All
pops up
right.
everywhere.
That's quite a collection, Ray.
Yeah. There's a lot more. There's a few that I should have had that I haven't got there, but it's hard to keep track of everything.
And most people, you've shared with me that sometimes you've given these talks and people walk out and say, I've never seen so many coincidences in my life.
Yeah, that's right. Yeah. I always tell them I've got more.
You've got more.
So I think the theme here today has been that that at all the large scales in the universe, from the sort of the planetary scale up to the galactic superclusters, we can see both evidence for spacings, regular spacings, and where we've got data, it shows the same time periods happen as cycles in different phenomena that may be related, maybe not. So those things show, I believe that I can say these things have now proved that my original hypothesis that there's standing waves in space that develop harmonics, that this is showing that there are electromagnetic waves in space, and that they really exist. Now, there's another thing that follows from that. Back in the 90s, I did some calculations on that, and there was one guy that was on the Usenet groups who did discuss with me quite well. He asked me lots of questions I answered, and he asked me about what. And I didn't feel he was anti. The one in the Bort forum was a little bit anti, but I see it now as a positive that they forced me to put more data together and make a good collection of things. And what he did, he said, what about, and he asked me questions, because we were looking at it as an alternative to the Big Bang. But it's not exactly an alternative to the Big Bang. It's really operating in a different domain. And we'll see that when we look at, there's some diagrams in the physics. There's a big triangle that shows the limit of GR, the limit of quantum mechanics, and the limit of harmonics theory, and how those fit together to explain everything over the very largest to the smallest distances and times and everything.
GR being general relativity?
Relativity, yeah, sorry, yeah.
Okay.
And eventually I've now come to the conclusion that probably the harmonics theory can explain why GR happens in a slightly different way to what they do. We don't need warp space, but let's leave that for later.
Okay.
What this one is about is the thing they call the missing mass problem. So back in the early 90s, they were talking about missing mass. The problem was that the rotation curves of galaxies didn't, at larger distances out from the center, the stars should be going around the galaxy slower. The velocity should pick up as you go out a bit and then gradually diminish. A galaxy is different to a solar system. In the solar system, nearly all the mass is in the sun. And so as you go further out, things go slower and slower and slower. But in the galaxy, a lot of the mass is spread out. So as you go away from the core, first of all, the velocities start to increase, level off, and then they start to decline. But they don't decline by nearly as much as they look like they should, according to how much matter we can see. So this has led to people inventing new theories of gravity and all sorts of things to try and explain that. But at larger scale still, there's still more problems. The speed at which galaxies move when there's clusters of galaxies, that indicates that has to be more missing mass. Otherwise, these clusters would fly apart. Now, I'm going to argue that some of that stuff isn't velocity. It's just changing in the red shift. But in the case of galaxies, they clearly are rotating. And so what's the problem? The problem is that if they're not taking account of the electromagnetic waves that the harmonics theory says exist at all scales, and they're causing the galaxy clusters, the galaxies, the stars, the planets, the moons, everything to form at different scales on the nodes of these waves. But those waves still continue to exist, and they have a lot of energy, huge amounts of energy. And so I had a stab. I thought, okay, I don't know. Harmonics theory works if the energy drops off as 1 over f, 1 over the frequency, or 1 over f squared, you get the same answer as harmonics theory works. But it seemed likely that 1 over f squared was the likely one for, because gravity and stuff do that, for the energy to drop off. And when I did that calculation and I took all those very big waves and worked them out, I got a reasonably good fit to the missing mass. And it starts off, I have trouble doing this, starts off and it comes down and goes out like that, the amount of missing mass. So there's a lot of missing mass at the larger scales. Well, those are the most huge electromagnetic standing waves. So they've got, according to me, they've got vast amounts of energy in them. And so we expect something different. So what we're getting to here is harmonics theory is taking away the need for what they now call dark energy and dark
matter.
Those two. As we get into the physics, we'll find it takes away about 4 or 5 other problems that people have had with things. So we drastically reduce, probably by 8 to 10 things, we probably reduce problems that existed previously, or things that people found that worked, but they've got no reason for. And so I reckon there's about 10 things cleared up. To be fair, after that, I'll have to say there's 1 or 2 things that are still mysteries, and I can't explain how they work. And I might have something wrong, and somebody else is going to have to work those out.
Well, if you can settle 10 out of 12 major mysteries, I'd say that's quite an accomplishment. So you mentioned some other scientists that were doing similar work. You mentioned Tift. Who are these other scientists?
Oh, okay. Tift was in California, and he did he worked on the 200 telescope. He was very highly regarded astronomer, had done a lot of great work. He made a catalogue of unusual galaxies, ones that did really weird stuff where galaxies were trying to do loops around, stretching each other out and doing weird stuff. So he made so these objects are called ARP, and the number in his catalogue of those. So he did that, and he did a lot of other stuff with the 200-inch, but he kept on saying, no, the Big Bang's wrong. And they didn't like that, and he kept publishing papers on that. And they ended up blocking him from using the 200-inch telescope anymore. So at that stage, he went to Germany and got a job over there and continued to do the work he was doing, but he didn't have the 200-inch telescope. When in the 90s, when I went to Europe, I arranged to see him, and I went to his place and met him in his office, and we had some discussions, and I told him about harmonics theory, and I told him how it would get the 72 kilometers per second and some other stuff like that, and he seemed sort of interested in that. I said to him, I would really have liked to have met Fred Hoyle as well, but unfortunately he died. He's an English astronomer, very, very bright guy. He had the alternate theory to the Big Bang for a while they called steady state, and they got discredited. And he accepted some things about it. Later on, he came up with another theory, which I haven't seen the details of, which was basically, instead of one Big Bang, had multiple creation events, he called them. Now, that fits you. I've shown you those graphs of those big intervals at which big things happen in the universe. So that would be consistent with what he's describing. But I have yet to find the information on that to compare that. So he's a very interesting one. Tift is an American astronomer. I exchanged a few emails with him, and I met him. Oh, now I haven't mentioned. When I mentioned Fred Hoyle, Arp said, well, there's going to be in Cardiff in 2 weeks' time, they're having a conference honouring Sir Fred Hoyle. I said, that's great. I'm going to be in Wales at that time. Give me more information. And I went to this conference. And so I met Tift there as well, and a few other ones that were famous in the what we might call the somewhat alternative astronomy world. So they are the guys that haven't gone along with the mainstream believing in the Big Bang. They've had alternatives. One guy didn't turn up at the to give his talk, so I offered to give a talk there and to fill in for him. And they said, you'll have to talk to Burbage. And I talked to him, and he wasn't going to allow it. He's also one of that group, but even after having been blocked and blocked and blocked by these mainstream ones, he blocked me. So I was a bit disappointed in that, because I think it would have been interesting for some of them. Another one there is Nalakar, And Fred Hoyle did work with a number of Indian astronomers, and they've done good work. Nalekar, we'll mention him with the problem of the red shift and why it's not a really a velocity thing, it's something different entirely. So he'll come up again. Who else? Tift, I should mention, when someone pointed me to Tift's paper, he had all the same stuff as what I had predicted. But after that, he got with another guy, Croft or something like that, and they developed a theory, which wasn't really theory, it was a mathematical formula that fitted some of the values and predicted some more. And after that, they started finding these other ones, but they hadn't found the other ones before that. So this is a danger when you have a theory and you do observations as well, that you may find things that agree with your theory. So we have to be warned of that. And I'm not trying to write Tift off. He did a lot of fantastic work. He got data on galaxy red shifts that were far more accurate than other people got. And with that, he was able to find these small ones. Most of the big analysis of galaxies are only accurate to size sort of like 20 or 30 kilometers per second. So you might find the 72 kilometer per second cycle, but you won't find those smaller ones. And he got them down to about 1. So that was very good stuff. So yeah, he'll get recognized better one day. There's a lot of people that I've come across that have done fantastic work, like Tift, who've been largely ignored, and they kept it up so much, eventually other people said, okay, we'll go and do the work to prove them wrong. And they went and did it and said, oh, we proved them right. The same thing will happen with a guy who took spheres up a mountain and measured the masses of them and how the weight changed as you went to higher altitude. Spheres made of different things, but hollowed out to have the same mass and the same diameter. He found different substances went differently when you took them up the mountain. This poor guy did loads and loads of experiments, and he took all the criticism and he did all the things that they said, and he did it right, and he did it, and he went up the mountain, did it, and eventually some other guy said, okay, poor fellow, I've got to go and find what he's doing wrong. And he went along and he said, no, he's not doing anything wrong. So these are other ways, and I don't know exactly how that fits into what I've done, but I think it's very important. I think it's important to follow it up further and work out why that's going on. So there's a lot of stuff. They make out like physics is nearly solved, but there's a lot of stuff in physics like that where things don't add up, and they just there's some very good books. I'm trying to remember the name of the guy. I've got one. It's stuff that doesn't fit in science. I'll find the name of the book and bring it up another time. And he and this guy had put one book out, which is from every different area. That's how I found about the 72 kilometers per second and thing in the first place. And he had so many interesting things there that basically scientists have said, yeah, that don't fit, put it over there. But then other people keep finding the same thing. So the same things are getting put over there. There's a great collection of them over there now. And then he did that one on all science, and then he did one on geology, one on biology, one on astronomy, one on this, one on that. And he's got about a set of about 10 of them. I haven't got all of those, I've just got the one. But I would recommend if you're starting a library for the Cycles Foundation, this guy's got a lot of stuff. Some of it's cycles, not a lot, but it's all stuff that's very interesting to help to tie the whole thing together.
Sounds interesting. Fantastic. Yeah. And what are we going to talk about next time, Ray?
I don't know. What have we got?
All right. Well, we'll give you some time.
I think we could go to the human scale. You saw those big intervals: Hubble scale, galaxy, stars, planets, moons. And then, did I miss one out? Anyway, there's 2 more there should be there at about a kilometer, about a mile, and at about 2 inches. And then the other ones after that go cell, atom, nucleon, quark, whatever you want to call it. Those middle ones, we don't see any obvious things at those scale, but in that range, there are some common measurements that turn up. And they're quite fascinating. They turn up in nature, and they turn up in things that humans have done. I don't know that I haven't put them in this category we just did, because I can't say that I can prove they're electromagnetic waves, but based on all the others, I think they're there. So so we'll find some unusual formations in rocks near cliffs that look like someone has made tiles and laid them there, but they're not. They're natural formations. And we'll find, and we'll look at the guy named Thom, who studied the stone circles in Britain and found that there were certain units that they seemed to prefer. And when I analysed his data, I found, yes, they are multiples and fractions of certain values, and these values just so happen to be the old imperial unit, less about 1%. So there's a few things like that going on. Yeah. So if we go the scale and through that, and then later on, we'll get down to the atomic scale and the subatomic particles and that, and they do exist. They are real, and there are patterns in them that people didn't notice. Although another fellow that I met in Russia, his name will come to me too. He did some different analysis to me, but also equally interesting in terms of patterns in the fundamental particles. So-called fundamental particles, not fundamental particles. They're less fundamental than economic cycles. We've got to get that one out. Someone please quote me. Economic cycles are just as fundamental as subatomic particles.
Let's talk about that more next time.
Yeah. Okay.
All right, Ray. Thank you so much. Great stuff. Bye.